Imagine you wake up tomorrow morning, reach for your coffee cup, and suddenly realize something mind-bending. Every single atom in that ceramic mug, every molecule of water, every particle that makes up the caffeine jolting you awake, all of it came from absolutely nothing. Not metaphorically nothing, not almost nothing, literally nothing. Right now, as you listen to these words, you're surrounded by roughly 10 to the 80th power atoms. That's a 1 followed by 80 zeros worth of fundamental building blocks, all swirling around you, through you, becoming you. And here's the thing that should make your brain tingle with curiosity. None of these atoms existed 13.8 billion years ago. Not a single one. Welcome back to another mind-expanding journey into the deepest mysteries of our universe. I'm absolutely thrilled you've decided to join me tonight as we dive headfirst into one of the most profound questions in all of science. How did everything come from nothing? And I mean everything. Every star burning in distant galaxies, every grain of sand on every beach, every thought racing through your mind right now. All of it traces back to a moment when atoms themselves had to be born from pure nothingness. Before we embark on this cosmic adventure together, please leave a comment and let me know where in the world you're tuning in from and what time it is in your corner of our pale blue dots. I'd also be incredibly grateful if you hit that like button and consider subscribing. Get ready, the story begins now. Tonight, we're not just talking about how atoms behave or what they're made of. We're going much deeper. We're traveling back to the very beginning, to a time when the concept of an atom was meaningless, because the universe itself was smaller than the period at the end of this sentence. We're going to witness the birth of matter itself. Watch as the fundamental forces of nature wrestled with pure energy to create the first protons, the first neutrons, the first electrons that would eventually dance together in the cosmic ballet we call chemistry. But here's where things get beautifully strange. The story of how atoms formed from nothing isn't just ancient history. It's happening right now in ways that will change how you see everything around you. By the time we're done tonight, you'll never look at a simple glass of water the same way again. You'll understand that every sip contains atoms forged in the heart of cosmic violence, particles that have journeyed across billions of years and countless light years just to quench your thirst. The journey we're about to take together spans scales so vast they challenge human comprehension. We'll start at the very beginning, in a realm where time itself might not have existed, where space was compressed into dimensions smaller than anything we can measure. We'll witness the universe's first breath, that explosive moment when everything we know began its incredible expansion from a point of infinite density and temperature. This isn't science fiction, though it certainly sounds like it. This is the cutting edge of cosmology, backed by decades of observations, mathematical models, and experiments that push the boundaries of human knowledge. We're living in an extraordinary time when scientists can actually trace the universe's history back to within a tiny fraction of a second after it all began. We can map the cosmic microwave background radiation, the afterglow of creation still echoing through space after nearly 14 billion years. But before we dive into the spectacular moment when atoms first assembled themselves from the chaos of the early universe, we need to understand what we're dealing with. What exactly is an atom? It's easy to think of them as tiny solid balls, like microscopic marbles rolling around and bumping into each other. That mental picture served scientists well for a while, but reality is far more mysterious and beautiful than those early models suggested. An atom is mostly empty space. If you could magnify an atom to the size of a football stadium, the nucleus would be smaller than a marble, sitting at the 50-yard line, while the electrons would be buzzing around somewhere in the upper reaches of the bleachers. Yet this mostly empty structure is what gives substance to everything solid you've ever touched, every breath of air you've ever drawn, every beam of light that's ever reached your eyes. The electrons aren't really orbiting like planets around a sun, despite what those familiar atomic diagrams suggest. They exist in probability clouds, regions where they might be found if you could somehow pin them down for measurement. They're simultaneously particles and waves, defying our everyday experience of how things should behave. This quantum weirdness isn't just some abstract scientific curiosity, it's the fundamental nature of reality, the strange rules that govern the universe at its most basic level. At the heart of each atom sits the nucleus, a dense cluster of protons and neutrons held together by forces so powerful they can overcome the electromagnetic repulsion between positively charged protons trying to push each other apart. The strong nuclear force, as physicists call it, is roughly 100 times more powerful than the electromagnetic force at these tiny scales. Without it, no nucleus larger than hydrogen could exist, and the universe would be a very different and much simpler place. These forces, these particles, these quantum mechanical behaviors that seem so alien to our daily experience, they all had to emerge from nothing. Not from some pre-existing material that got rearranged, not from energy that was already floating around, waiting to be organized, from absolutely nothing at all. The very idea challenges everything our brains are wired to understand. We live in a world where everything comes from something else. Wood comes from trees, trees come from seeds, seeds come from earlier trees in an endless cycle of transformation. Even in our most advanced laboratories, when we create new elements or discover exotic particles, we're always starting with something, transforming existing matter and energy into new configurations. But the universe itself appears to have bootstrapped its way into existence, pulling itself up by cosmic bootstraps that didn't even exist yet. This isn't just a philosophical puzzle or a gap in our knowledge waiting to be filled. It's a fundamental feature of reality that forces us to expand our understanding of what's possible. The mathematics that describe this cosmic genesis are as beautiful as they are mind-bending. Equations that connect the largest structures in the universe to the behavior of the smallest particles. Formulas that predict the abundance of different elements with stunning accuracy. Theoretical frameworks that allow us to peer back through time and space to witness creation itself. But mathematics alone can't capture the full wonder of what we're exploring tonight. There's something almost magical about the realization that the carbon atoms in your body were forged in the nuclear furnaces of dying stars, that the oxygen you breathe was created when massive suns exploded in cosmic violence beyond imagination, scattering their atomic creations across the galaxy like cosmic seeds waiting to grow into planets, life, and consciousness. Every atom in your body is a time traveler, a survivor of cosmic catastrophes, a witness to the universe's 14 billion-year journey from simplicity to complexity. The hydrogen in your water molecules remembers the universe when it was less than 20 minutes old. The heavier elements in your bones and blood carry memories of stellar death and rebirth, of cosmic recycling programs that operate on scales of space and time that dwarf human history. Tonight, we're going to follow that incredible journey step by step. We'll start at the very beginning, in the first moments when the universe was so hot and dense that atoms couldn't exist, when matter and energy were locked in a cosmic dance of creation and annihilation. We'll watch as the universe expanded and cooled, creating the conditions where the first atomic nuclei could form and survive. We'll witness the cosmic dark ages, when the universe was filled with naked atomic nuclei and free electrons, too hot for stable atoms to exist, opaque to light and shrouded in cosmic fog. And then we'll see the moment of cosmic dawn, when the universe finally cooled enough for electrons and nuclei to combine into the first neutral atoms, allowing light to travel freely through space for the first time. This story isn't just about the distant past, it's about the ongoing miracle of atomic stability, the delicate balance of forces that allows the matter around you to maintain its structure across cosmic time. It's about the quantum mechanical principles that prevent electrons from spiraling into atomic nuclei, the nuclear physics that keeps protons and neutrons bound together despite their mutual repulsion, the electromagnetic interactions that allow atoms to link up into molecules and build the complex chemistry that makes life possible. We're about to embark on the greatest detective story ever told, using clues written in starlight and cosmic radiation to reconstruct events that happened when the universe was younger than a human heartbeat. We'll see how scientists have pieced together this incredible narrative through careful observation, brilliant theoretical insights, and experiments that recreate conditions from the first moments of cosmic history. The journey ahead will challenge your intuitions about time, space, matter, and energy. We'll encounter concepts that seem to violate everything you thought you knew about cause and effect, explore realms where the normal rules of physics break down, and discover that the universe is far stranger and more wonderful than anyone could have imagined just a century ago. But here's the most amazing part. This isn't just an academic exercise or a collection of abstract facts to memorize. This is your origin story, the story of how you personally came to exist. Not just how your parents met or how life evolved on Earth, but how the very atoms that make up your body were created from nothing at all and assembled through cosmic processes into the thinking, feeling, wondering being that's listening to these words right now. So settle in, take a deep breath of that ancient hydrogen and stellar oxygen, and prepare to have your mind expanded by the most incredible, true story ever discovered. The story of how atoms formed from nothing, how something came from nothing, and how nothing turned out to be far more interesting than anyone ever suspected. The universe is about to reveal its deepest secrets, and you have front row seats to the greatest show in existence. Let's begin our journey back to the very beginning of everything. Our story begins in a realm so extreme, it defies every intuition we've developed about how reality works. We're talking about the first fleeting moments after the Big Bang, when the entire observable universe was compressed into a space smaller than a proton, heated to temperatures that would make the core of the hottest stars seem like frozen tundra. Picture this impossibility. Everything you can see, everything that exists in all directions, as far as the most powerful telescopes can peer, all of it squeezed into a point so tiny that comparing it to an atom would be like comparing a grain of sand to the entire Earth. The temperature at this moment reached levels that our brains simply cannot process. We're talking about 10 to the 32nd power Kelvin. That's a 1 followed by 32 zeros worth of heat. Temperatures so extreme that the very concepts of matter and energy become meaningless. At these incomprehensible conditions, the fundamental forces that govern our universe today were unified into a single, primordial superforce. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, all the players that would eventually choreograph the cosmic dance of atoms, were indistinguishable from each other. It was like having all the instruments of a symphony orchestra playing the exact same note at volumes that would shatter reality itself. But here's where the story becomes even more mind-bending. This wasn't just hot and dense. This was a state of existence where the normal flow of time itself breaks down. Our best theories suggest that time, as we understand it, might not have even existed in any meaningful way. The mathematics that describe these first moments predict what physicists call a singularity, a point where our equations literally break down and start spitting out infinities. Now, most physicists don't believe the universe actually reached infinite density and temperature. Instead, they suspect that our current understanding of physics simply isn't sophisticated enough to describe what really happened at the very beginning. We need a theory that successfully marries quantum mechanics, which governs the behavior of the incredibly small, with general relativity, which describes gravity and the large-scale structure of space-time. But here's what we do know with remarkable confidence. Something extraordinary happened around 10 to the negative 36th seconds after the beginning, That's a decimal point followed by 35 zeros and then a 1. At this moment, the universe underwent what cosmologists call cosmic inflation, the most rapid expansion in the history of existence. In a time span so brief that it makes the blink of an eye seem like an eternity, the universe expanded by a factor that staggers the imagination. We're talking about growth from the size of a subatomic particle to roughly the size of a grapefruit, all happening faster than you could snap your fingers. In fact, this expansion occurred so quickly that it actually exceeded the speed of light, something that sounds impossible until you realize that it wasn't matter moving through space, but space itself expanding. This cosmic inflation explains one of the most puzzling observations about our universe. When we look out in all directions, we see that the cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature everywhere we look. This seems impossible because regions of space that are separated by vast distances should never have been able to communicate with each other, never had time to reach thermal equilibrium. But inflation solves this puzzle beautifully. Before inflation, all these apparently disconnected regions were actually in close contact, able to reach the same temperature before being stretched apart by the explosive expansion. As inflation ended, around 10 to the negative 33rd seconds, the universe entered what physicists call the electroweak epoch. The temperature had dropped to a merely incomprehensible 10 to the 15th Kelvin, cool enough for the unified superforce to begin splitting apart. The strong nuclear force separated first, followed by the electromagnetic and weak forces breaking apart from each other. This separation wasn't just some abstract reshuffling of cosmic bookkeeping. It was the moment when the fundamental architecture of reality, as we know it, began to take shape. The forces that would eventually allow protons to stick together in atomic nuclei, that would permit electrons to orbit those nuclei without spiraling inward, that would enable the complex chemistry of life itself. All of these began to assume their distinct identities. But we still don't have atoms yet. We don't even have the building blocks of atoms. The temperature is still so extreme that even protons and neutrons cannot exist as stable entities. Instead, the universe is filled with what physicists call a quark-gluon plasma, a seething ocean of the most fundamental particles we know about, held together by forces so intense they beg a description. Quarks are the building blocks of protons and neutrons, but in this early cosmic furnace, they can't combine into these familiar particles. The temperature is simply too high, the energy too intense. It's like trying to build a house during a tornado made of fire. Every time quarks attempt to bind together through the strong nuclear force, the thermal violence tears them apart again. The gluons, meanwhile, are the force-carrying particles that mediate the strong nuclear force. They're the cosmic glue that will eventually hold quarks together inside protons and neutrons. But at these temperatures, even they can't establish stable connections. The entire universe resembles a cosmic soup where the ingredients for matter exist but cannot yet combine into anything we would recognize as substantial. As the universe continues to expand, it also continues to cool. This isn't the gentle cooling you might experience stepping outside on a winter evening. This is a fundamental transformation in the nature of reality itself, as the available energy drops below critical thresholds that allow new forms of organization to emerge. Around 1 microsecond after the Big Bang, when the temperature has fallen to about 10 to the 13th Kelvin, something remarkable happens. The universe finally becomes cool enough for quarks to bind together into protons and neutrons. This transition, called the QCD phase transition, marks the birth of the particles that will form the nuclei of all future atoms. Picture this moment as cosmic alchemy on an unimaginable scale. Suddenly, the chaotic quark-gluon plasma begins to organize itself into discrete packages. 2 up quarks and 1 down quark bind together to form protons, each carrying a positive electric charge. 2 down quarks and 1 up quark combine to create neutrons, electrically neutral, but slightly more massive than their proton cousins. This mass difference between protons and neutrons, tiny though it is, will prove crucial for the future development of the universe. It's one of those seemingly minor details that turns out to have the future. The strong nuclear force that binds core cosmic significance, determining the eventual ratio of hydrogen to helium in the universe together inside protons and neutrons, is unlike anything we encounter, and setting the stage for stellar formation billions of years in our everyday experience. It actually grows stronger as quarks are pulled apart, rather than weaker like every other force we know. Try to separate quarks beyond a certain distance, and the energy required becomes so intense that it creates new quark-antiquark pairs rather than achieving separation. It's as if the universe itself refuses to allow quarks to exist in isolation. But even with protons and neutrons now populating the cosmic scene, we still can't have atoms. The temperature is still far too high for electrons to remain bound to nuclei. Any electron that attempts to settle into orbit around a proton gets immediately blasted away by the intense thermal radiation filling space. The universe at this stage resembles a cosmic storm of naked atomic nuclei and free electrons, all bouncing around in violent thermal motion. The electrons themselves present their own fascinating story. Unlike protons and neutrons, which are composed of quarks, electrons appear to be fundamental particles with no internal structure that we can detect. They're point-like entities that carry electric charge and spin, participating in the electromagnetic and weak nuclear forces, but remaining immune to the strong force that binds quarks together. These electrons were created earlier in the cosmic timeline through processes that transformed pure energy into matter and antimatter pairs. For every electron created, an antimatter twin called a positron also came into existence. In a perfectly symmetric universe, all these particles and antiparticles should have annihilated each other completely, leaving nothing but pure energy behind. But our universe harbours a subtle asymmetry, a slight preference for matter over antimatter, that remains one of the deepest mysteries in physics. For every billion antimatter particles created in the early universe, there were about 1,000,000,001 matter particles. This tiny imbalance, this cosmic rounding error, is the reason anything exists at all. After all the matter and antimatter annihilated each other in spectacular bursts of gamma radiation, that leftover fraction of matter particles remained to build everything we see today. The scale of this annihilation was beyond anything we can readily comprehend. Imagine every particle in the observable universe paired with an antiparticle twin, both vanishing in pure energy release. The universe was literally lighting itself up from the inside, converting mass into radiation in quantities that dwarf the output of every star that has ever shone. Yet through this cosmic conflagration, that precious remnant of matter survived. The electrons that would eventually orbit atomic nuclei, the protons that would form hydrogen atoms, the neutrons that would enable the creation of heavier elements, all of them are survivors of this primordial holocaust, the victors in a battle between existence and oblivion that was decided by the slimmest of margins. As the universe continued its relentless expansion and cooling, we approach another crucial threshold in our story. The temperature is dropping toward levels where atomic nuclei can begin to form, where protons and neutrons can stick together despite the electromagnetic repulsion between positively charged protons. This process, called Big Bang nucleosynthesis, represents the universe's first attempt at chemistry, though it's chemistry unlike anything you'd recognize from your high school textbook. Instead of gentle molecular interactions, we're dealing with nuclear processes that require temperatures of billions of degrees, energies that can overcome the fundamental forces holding matter apart. The neutrons, unstable when left alone, begin to decay into protons through a process mediated by the weak nuclear force. A neutron transforms into a proton, an electron, and a nearly massless particle called a neutrino. This decay would eventually eliminate all neutrons from the universe if they couldn't find partners, but the high-energy environment allows some neutrons to bind with protons before they can decay. When a proton and neutron successfully combine, they form the nucleus of heavy hydrogen, called deuterium. This is an incredibly delicate process, requiring precise conditions of temperature and density. Too hot, and the thermal radiation tears the newly formed nucleus apart before it can stabilize. Too cool, and the particles lack the energy needed to overcome their mutual repulsion and bind together. The universe threads this needle with exquisite precision, creating a window of opportunity lasting only a few minutes, during which nuclear synthesis can occur. In this brief cosmic moment, roughly 25% of all the protons in the universe combine with neutrons to form helium nuclei, each containing 2 protons and 2 neutrons bound together by the strong nuclear force. Smaller amounts of deuterium, tritium, and lithium also form during this period, but the expanding universe cools too quickly for more complex nuclei to assemble. The process grinds to a halt when the temperature drops below the threshold needed for nuclear fusion, leaving the universe with a specific mixture of light elements that matches observations with startling accuracy. This cosmic cooking session lasts only about 20 minutes, but its products will endure for billions of years. The helium created during Big Bang nuclear synthesis still comprises roughly 25% of all ordinary matter in the universe today, exactly as predicted by our theoretical models. It's one of the great triumphs of modern cosmology, a precise quantitative prediction that matches observation across the entire observable universe. But we still don't have atoms. We have atomic nuclei swimming in a sea of free electrons, but the temperature is still too high for these components to combine into neutral atoms. The universe remains opaque to light, a cosmic fog where photons can't travel more than a tiny distance before being scattered by free electrons. This fog-bound era will persist for hundreds of thousands of years, a cosmic dark age when the universe was filled with matter but remained invisible to any hypothetical observers. The stage is set for atomic formation. All the players are in position, but the final act of our cosmic drama must wait for the universe to cool just a little bit more. The atoms that will eventually form your body, that will become the air you breathe and the ground beneath your feet, are still centuries of millennia away from their moment of birth. But the foundation has been laid, the nuclear building blocks are in place, and the universe continues its patient expansion toward the moment when electrons and nuclei can finally unite in stable neutral atoms. That moment, when it comes, will flood the universe with light for the first time, marking the end of the cosmic dark ages and the beginning of the era when matter can begin organizing itself into the complex structures that will eventually give rise to stars, planets, and life itself. The cosmic clock keeps ticking, and we're approaching one of the most extraordinary moments in the history of existence. Picture the universe as it exists roughly 400,000 years after the Big Bang. It's still unimaginably hot by earthly standards, hovering around 3,000 degrees Kelvin. But this represents a dramatic cooling from those first blazing moments we just witnessed. At this temperature, something magical is about to happen. For the first time since the universe began, conditions are becoming just right for electrons and atomic nuclei to dance together in stable partnerships. We're about to witness the birth of the very first atoms, and with them, the transformation of our cosmos from an opaque, fog-shrouded realm into a transparent universe where light can finally travel freely across vast distances. This moment has a beautiful name in cosmology, recombination, though technically it should be called combination, since electrons and nuclei are meeting for the first time rather than reuniting. But the name has stuck, and there's something poetic about it. After hundreds of thousands of years of separation, the fundamental building blocks of matter are finally ready to recombine into something greater than the sum of their parts. Before this moment, every photon in the universe was trapped in an endless game of cosmic pinball. Light couldn't travel more than a few meters before colliding with a free electron, getting scattered in a random direction, only to immediately hit another free electron and bounce again. The universe was like a cosmic fog so thick that even if stars had existed, which they didn't, you wouldn't have been able to see your hand in front of your face. But as the temperature drops below that critical threshold of 3000 Kelvin, electrons begin losing their frantic thermal energy. They're no longer moving fast enough to escape when they wander close to the electromagnetic pull of an atomic nucleus. It's like watching cosmic snowflakes form as the universe cools, with electrons settling gently into stable orbits around protons and helium nuclei. The process doesn't happen all at once across the entire universe. Instead, it unfolds like a wave of organization spreading through space, transforming chaos into order one atom at a time. In regions where the density is slightly higher, recombination occurs first. In emptier regions, it takes a bit longer. This slight variation in timing will prove crucial billions of years later, when these density differences grow into the cosmic web of galaxies and empty voids that structure our universe today. When that first hydrogen atom forms, when that first electron settles into its quantum mechanical dance around a proton, something unprecedented occurs. The photon that had been bouncing between free charges suddenly finds itself in a universe where most electrons are bound up in neutral atoms. With dramatically fewer free electrons to scatter off, light can finally travel in straight lines across cosmic distances. This liberation of light marks one of the most significant transitions in cosmic history. In a relatively brief period, cosmically speaking, the universe transforms from opaque to transparent. The cosmic microwave background radiation that we detect today is the afterglow of this moment. The last light scattered by free electrons before atoms formed and the fog lifted forever. But let's focus on those first atoms themselves, because they're about to become the protagonists of our story. The hydrogen atom, consisting of a single proton embraced by a single electron, becomes the universe's most abundant creation. These simple atoms make up roughly 75% of all the ordinary matter that will ever exist. Every hydrogen atom in your body, in the water you drink, in the vast interstellar clouds between stars, traces its lineage back to these first moments of atomic formation. The helium atoms tell an equally fascinating story. With 2 protons and 2 neutrons in their nuclei, they require 2 electrons to achieve neutrality. These more complex atoms represent about 25% of ordinary matter, and their formation during recombination creates the first examples of what we might call atomic diversity. The universe is no longer monotonous. It now contains 2 distinct types of atoms, each with its own unique properties and potential for future chemistry. There's something almost miraculous about the quantum mechanics that allow these first atoms to remain stable. Classical physics would predict that electrons should spiral into the nucleus, radiating energy and causing atoms to collapse in a tiny fraction of a second. But quantum mechanics saves the day with its strange rules about allowed energy levels and the uncertainty principle. Each electron in an atom can only exist in specific, quantized energy states. It's as if the universe has invisible steps built into it, and electrons can only stand on these steps, never between them. The lowest step, called the ground state, represents a perfect balance between the electron's kinetic energy and its attraction to the nucleus. The electron literally cannot fall any lower because there is no lower energy level available to it. This quantum mechanical stability is what makes chemistry possible. Without it, atoms would be fleeting, unstable entities that could never persist long enough to combine into molecules, let alone complex structures like proteins or DNA. The universe would remain forever simple, forever boring, forever incapable of generating the complexity that leads to stars, planets, and eventually consciousness itself. As recombination sweeps across the cosmos, we're witnessing the universe's first great phase transition since the moments immediately after the Big Bang. The change is as dramatic as water freezing into ice, but instead of a change in molecular arrangement, we're seeing a fundamental transformation in the very nature of matter itself. The newly formed atoms don't just sit there passively. They immediately begin interacting with each other through gravitational attraction. Remember, gravity is an incredibly weak force on atomic scales, but it's also the only force that acts over truly cosmic distances without diminishing. Every hydrogen atom pulls on every other hydrogen atom, no matter how far apart they are. These gravitational interactions are almost imperceptibly tiny at first, but they're persistent and cumulative. Regions of space that happen to have slightly more matter than average begin attracting additional matter from their surroundings. Over millions of years, these tiny density fluctuations will grow into the seeds of cosmic structure, the birthplaces of the first stars. But we're getting ahead of ourselves. For now, let's appreciate what has just occurred. The universe has just become a place where stable matter can exist, where the fundamental building blocks of complexity have taken their first tentative steps toward organization. We have atoms, real atoms, with electrons orbiting nuclei in stable configurations that will persist for billions of years. These atoms are still incredibly simple by the standards of what's to come. We have hydrogen and helium, period. No carbon, no oxygen, no iron, no silicon. None of the heavier elements that will eventually make planets possible, that will enable the rich chemistry of life. Those elements are still locked away in the future, waiting to be forged in the nuclear furnaces of the first stars. But even these simple atoms represent a monumental achievement. They are the universe's first successful attempt at building stable, complex structures from simpler components. They demonstrate that the laws of physics, those fundamental rules that govern how particles interact, are capable of generating order from chaos, complexity from simplicity, something from nothing. The electromagnetic force that holds electrons in their atomic orbits is the same force that will eventually enable atoms to link together into molecules. The quantum mechanical rules that stabilize these first atoms will govern all future chemistry. The gravitational attraction between atoms will grow into the force that builds stars and galaxies. In these first atoms, we can already see the seeds of everything that will follow. The hydrogen that will fuel the first stars, providing the energy source that powers stellar nucleosynthesis and creates heavier elements. The helium that will serve as the end product of hydrogen fusion, signaling when stars have exhausted their primary fuel source. The gravitational clumping that will eventually pull matter together into the dense cores where nuclear fusion can ignite. The universe has just taken its first major step toward becoming the rich, complex, fascinating cosmos we inhabit today. From a state where stable matter was impossible, we've transitioned to a realm where atoms can exist indefinitely, where the building blocks of complexity are finally available for construction projects that will span cosmic time. This is the moment when the universe stops being just about fundamental physics and starts becoming about chemistry, about structure, about the endless possibilities that emerge when simple components combine in creative ways. We're still hundreds of millions of years away from the first stars, billions of years from the first planets, but the foundation has been laid. The atoms floating through space in the aftermath of recombination don't know that they're destined to become part of stellar cores, planetary atmospheres, or eventually the bodies of conscious beings who will contemplate their own atomic origins. They're just following the laws of physics, responding to forces moving through space according to the gravitational choreography that will shape cosmic evolution, but we know their future, and it's spectacular. These simple atoms, born in the cooling aftermath of the Big Bang, will participate in cosmic processes that transform them into every element on the periodic table. They'll witness the birth and death of stars, the formation of galaxies, the emergence of planets capable of harboring life. Some of these very atoms, the ones forming right now in our cosmic narrative, will eventually find themselves incorporated into your body, carrying the memory of recombination in their quantum mechanical structure. The hydrogen in your water molecules, the helium that was once dissolved in your bloodstream during a medical procedure, they all trace their existence back to this moment when electrons and nuclei first found each other in the cooling universe. We're witnessing the birth of atomic matter as a permanent feature of cosmic architecture. Before this moment, atoms were impossible. After this moment, they become the fundamental currency of cosmic complexity, the building blocks from which everything else will be constructed. The universe has just learned how to make atoms from nothing, and it will never forget this lesson. From this point forward, atomic matter will be a persistent feature of reality, the foundation upon which all future complexity will be built. The age of atoms has begun, and with it, the universe has taken its first major step toward becoming the magnificent, complex, life-bearing cosmos we call home. Now, as these first atoms drift through the cosmic darkness, something extraordinary begins to unfold. The universe has just learned its first lesson in construction, but it's about to discover that atoms are merely the opening chapter in a much grander story of creation. Picture the cosmos at this moment. We're roughly 400,000 years past the Big Bang, and space stretches endlessly in all directions, filled with a thin soup of hydrogen and helium atoms. The temperature has dropped to a mere 3,000 Kelvin, practically Arctic compared to those first blazing moments. But this cooling universe is far from dormant. It's pregnant with potential, ready to give birth to structures that will dwarf anything we've seen so far. The atoms floating through this primordial space aren't distributed evenly. Quantum fluctuations from the inflationary epoch have left their fingerprints on the cosmic fabric, creating regions where matter is slightly more concentrated and others where it's slightly more sparse. These density variations are incredibly subtle, differences of only 1 part in 100,000, but they represent the seeds from which cosmic architecture will grow. Gravity, that patient sculptor of the universe, begins its slow but inexorable work. Every atom pulls on every other atom with a force so weak it seems almost negligible. But gravity has 2 crucial advantages over every other force in nature. It never stops pulling, and it never gets tired. While electromagnetic forces can be shielded and nuclear forces operate only at microscopic scales, gravity reaches across the vast emptiness of space with infinite patience and unlimited endurance. In those regions where atoms happen to be slightly more concentrated, gravitational attraction begins to win a cosmic tug-of-war. More matter attracts even more matter in a process that feeds on itself. It's like watching cosmic snowballs grow as they roll downhill, gathering more material with each passing millennium. But this isn't the gentle accumulation you might imagine. We're dealing with processes that operate across scales so vast they challenge human comprehension. Individual atoms might drift for millions of years before encountering enough neighbours to feel significant gravitational pull. The universe has all the time in existence to work with, and it uses every second. As these gravitational seeds continue to grow, they begin carving structure into what was once smooth space. Matter flows along invisible highways of gravitational attraction, creating a cosmic web of filaments and voids that will persist for billions of years. The universe is learning architecture, discovering how to build with atoms, the way a master craftsman learns to work with wood or stone. The process accelerates as matter becomes more concentrated. Gravitational attraction grows stronger as more atoms cluster together, pulling in material from ever greater distances. What started as barely perceptible density fluctuations evolve into genuine concentrations of matter, proto-galactic clouds that span hundreds of thousands of light years. Inside these growing clouds, something remarkable happens. As atoms fall inward, under their mutual gravitational attraction, they begin to speed up. The gravitational potential energy of their elevated positions converts into kinetic energy of motion. The atoms start moving faster, colliding more frequently, and most importantly, heating up. This heating represents a fundamental transformation in the nature of cosmic evolution. For the first time since recombination, thermal energy begins to compete with the cooling expansion of the universe. Local regions of space start getting warmer rather than cooler, setting the stage for processes that require enormous temperatures to operate. The hydrogen and helium atoms spiraling inward in these collapsing clouds don't realize they're participating in one of the most crucial transitions in cosmic history. They're simply following the laws of physics, responding to gravitational forces, converting potential energy into kinetic energy according to rules established in the first moments after the Big Bang. But we can see where this process is heading. These atoms are unwittingly constructing the furnaces that will forge every other element in the periodic table. They're building the stellar nurseries where nuclear fusion will transform hydrogen into helium, helium into carbon, carbon into oxygen, and so on, up the atomic ladder to create the rich diversity of elements that makes complex chemistry possible. The collapse continues for millions of years, with matter streaming inward from distances measured in light years. Temperatures in the densest regions climb from 3,000 Kelvin to 10,000, then 100,000, then 1,000,000 degrees. The atoms that once drifted peacefully through empty space now find themselves in an increasingly violent thermal environment. At these rising temperatures, something fascinating begins to happen to atomic structure itself. The electrons that had settled so comfortably into their quantum mechanical orbits around nuclei start getting excited into higher energy states. Collisions between atoms become energetic enough to knock electrons completely free from their nuclei, reversing the process of recombination that had occurred hundreds of millions of years earlier. But this isn't a return to the cosmic fog of the early universe. This time, the ionization is localized, confined to specific regions where gravitational collapse has concentrated matter and raised temperatures. The universe is developing structure, creating places where conditions are dramatically different from the cold emptiness of intergalactic space. As the collapse continues and temperatures soar even higher, we approach another critical threshold. When the core temperature of these collapsing clouds reaches roughly 10 million Kelvin, something extraordinary occurs. The thermal energy becomes so intense that it can overcome the electromagnetic repulsion between atomic nuclei. Hydrogen nuclei, which are just lone protons, begin moving fast enough to crash into each other with sufficient force to trigger nuclear fusion. This isn't the gentle chemistry of electron orbital interactions we saw during recombination. This is nuclear alchemy, the transformation of one element into another through processes that release enormous amounts of energy. When 4 hydrogen nuclei manage to combine into a single helium nucleus through a complex series of reactions, they release energy in the form of gamma radiation, positrons, and neutrinos. But here's the crucial detail that makes stellar fusion possible. The mass of the helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei that created it. That missing mass doesn't simply disappear. According to Einstein's famous equation, E equals mc squared, it converts directly into energy. A tiny amount of matter becomes a tremendous amount of energy, enough to power stellar fusion reactions for billions of years. This energy release creates radiation pressure that pushes outward against the inward pull of gravity. For the first time in cosmic history, we have a force capable of balancing gravitational collapse. The result is a stable, self-regulating system where nuclear fusion generates exactly enough outward pressure to counteract gravitational compression. Congratulations! The universe has just ignited its first star. This moment represents a phase transition as dramatic as anything we've witnessed in our cosmic journey so far. We've gone from a universe filled with simple atoms drifting through empty space to one where nuclear furnaces burn at temperatures of millions of degrees, converting hydrogen into helium and releasing the energy that will make all future complexity possible. But the birth of the first star is just the beginning of stellar nucleosynthesis, the process that will populate the periodic table with elements heavier than hydrogen and helium. Inside stellar cores, where temperatures reach tens of millions of degrees and pressures exceed anything imaginable on Earth, atomic nuclei participate in a cosmic cooking process that creates the chemical diversity necessary for planets, life, and consciousness. The helium created by hydrogen fusion doesn't just sit there passively. In the most massive stars, core temperatures eventually become hot enough for helium nuclei to fuse together, creating carbon in a process that requires 3 helium nuclei to collide almost simultaneously. This triple alpha process, as physicists call it, is so improbable that it seems miraculous it occurs at all. Yet occur it does, and the carbon nuclei produced by helium fusion become the raw material for even more exotic nuclear reactions. Carbon can fuse with helium to create oxygen. Oxygen can combine with helium to produce neon. The stellar forge continues working its way up the periodic table, creating silicon, sulfur, phosphorus, and eventually iron. Each step in this nucleosynthetic ladder requires higher temperatures and pressures than the last. The star must burn through its fuel supplies in successive shells, first converting hydrogen to helium in its core, then helium to carbon when the hydrogen is exhausted, then carbon to heavier elements in an increasingly frantic attempt to maintain the energy output needed to prevent gravitational collapse. The atoms being forged in these stellar furnaces have no idea they're participating in the creation of cosmic complexity. They're simply responding to the extreme conditions inside stellar cores, following the laws of nuclear physics wherever those laws lead them. But we can appreciate the profound significance of what's occurring. Every carbon atom that will eventually become part of your DNA is being forged right now in these first stellar cores. Every oxygen atom that you'll breathe, every calcium atom that will strengthen your bones, every iron atom that will carry oxygen in your bloodstream, all of them are products of stellar nucleosynthesis occurring in the first generation of stars. This process continues for millions of years, with each star serving as a cosmic alchemy laboratory, transforming the simple hydrogen and helium left over from the Big Bang into the rich diversity of elements that will make planets and life possible. But stellar nucleosynthesis faces a fundamental limitation that will prove crucial for the future evolution of cosmic complexity. Iron represents a nuclear dead end. Elements lighter than iron release energy when they fuse together, providing the fuel that powers stellar reactions. But iron nuclei are so tightly bound that fusing them together actually requires energy rather than releasing it. When a massive star's core fills with iron, nuclear fusion can no longer generate the radiation pressure needed to balance gravitational collapse. What happens next is one of the most violent events in the universe, a core collapse supernova. The iron core, no longer supported by fusion reactions, collapses in a fraction of a second from the size of Earth to the size of a city. The gravitational energy released by this collapse is so enormous that it reverses the infall and blows the star apart in an explosion that briefly outshines an entire galaxy. But this stellar death serves a crucial purpose in cosmic evolution. The supernova explosion creates conditions even more extreme than stellar cores, temperatures and pressures sufficient to forge elements heavier than iron through rapid neutron capture processes. Gold, platinum, uranium, and all the other elements beyond iron in the periodic table are created in these moments of stellar destruction. More importantly, the supernova blast wave hurls all the elements created during the star's lifetime out into space, seeding the interstellar medium with the chemical diversity necessary for future planet formation. The carbon, oxygen, silicon, and iron that took millions of years to create in stellar cores are scattered across light years of space in a matter of hours. This element dispersal represents another crucial phase transition in cosmic evolution. We've gone from a universe containing only hydrogen and helium to one where space itself is enriched with the full spectrum of elements needed for rocky planets, complex chemistry, and eventually life itself. The atoms blown into space by supernovae don't remain isolated for long. Gravity continues its patient work, pulling this enriched material back together into new generations of stars, and for the first time in cosmic history, planetary systems. The second and third generation stars that form from this enriched material have access to the full periodic table, enabling them to develop the solid planets where complex chemistry can occur. The universe has learned how to make atoms from nothing, how to build stars from atoms, how to forge new elements in stellar cores, and how to distribute those elements through space via stellar explosions. Each step in this process has opened up new possibilities for complexity, new ways for matter to organize itself into increasingly sophisticated structures. We're now roughly 1 billion years past the Big Bang, and the cosmos has become almost unrecognizably complex compared to those first moments when even atoms were impossible. We have galaxies filled with billions of stars, planetary systems with rocky worlds, and interstellar space enriched with every element necessary for the chemistry of life. But the story of atomic formation is far from over. Those elements scattered by dying stars will eventually condense into new worlds where atoms can experiment with molecular combinations impossible in the extreme environments of stellar cores. They'll discover how to build proteins and DNA, how to create the complex molecular machinery that enables life to emerge from non-living matter. The atoms in your body right now are veterans of this cosmic journey. They've survived the violence of stellar cores, the explosive fury of supernova, the patient accumulation of planetary formation, and billions of years of geological and biological evolution. They carry within their quantum mechanical structure the entire history of the universe, from the first moments after the Big Bang to the present day. Tonight, as you contemplate these words, you're not just learning about atomic formation. You're communing with the universe's deepest creative processes, recognizing your intimate connection to cosmic evolution itself. The atoms that make up your thoughts, the ones processing these ideas right now, they're not separate from the universe's story of creation. They are that story, living and breathing and thinking its way toward ever greater complexity and understanding. The universe has just discovered something profound about itself. It has learned that destruction can be an act of creation, that violence can serve beauty, that endings can become beginnings on scales that dwarf human imagination. Those scattered atoms hurled across space by dying stars carry with them the potential to build worlds we can barely comprehend. Picture this cosmic recycling program operating on timescales that make geological epochs seem like heartbeats. The carbon forged in stellar cores drifts through space for millions of years, joining vast molecular clouds that span hundreds of light years. These aren't the empty voids you might imagine when you think of outer space. They're cosmic nurseries, rich with the chemical diversity that makes complexity possible. In these interstellar clouds, atoms encounter conditions they've never experienced before. The temperature drops to just a few degrees above absolute zero, so cold that even helium freezes solid. The density is so low that a cubic meter might contain fewer atoms than a single breath of air on Earth. Yet in this seemingly barren environment, something remarkable begins to happen. For the first time since those early moments After the Big Bang, atoms have the opportunity to engage in gentle chemistry rather than violent nuclear reactions. Without the crushing pressures and searing temperatures of stellar cores, electrons can once again play their delicate dance around atomic nuclei, forming the chemical bonds that will eventually enable molecular complexity. Hydrogen atoms, the universe's most abundant creation, begin linking up with other elements to form simple molecules. Water forms when hydrogen meets oxygen, creating H2O molecules that will eventually become the solvent for life's chemistry. Carbon monoxide emerges from the marriage of carbon and oxygen, while hydrogen cyanide brings together hydrogen, carbon, and nitrogen in combinations that hint at the organic chemistry to come. These molecular formation processes occur with exquisite slowness compared to the nuclear furnaces of stars. Individual atoms might drift through space for thousands of years before encountering the right partner for a chemical reaction. But the universe has patience, and these interstellar clouds have lifespans measured in tens of millions of years. As more complex molecules form, they begin to stick to tiny grains of cosmic dust, creating microscopic laboratories where surface chemistry can occur. These dust grains, smaller than the wavelength of visible light, serve as meeting places where atoms can encounter each other more frequently than they would in the vast emptiness of space. On the surfaces of these dust grains, protected from the harsh radiation that would destroy them in open space, molecules can grow in complexity. Simple two-atom combinations link up to form chains and rings, creating the first organic compounds to exist since the universe began. Methane, ammonia, and even more complex hydrocarbons begin to populate these molecular clouds. But we're still talking about incredibly simple chemistry compared to what's coming. These early molecules are like the first hesitant words in a language that will eventually produce poetry and philosophy. They represent the universe's initial experiments with the kinds of chemical bonds that will one day enable DNA to store information and proteins to catalyze the reactions of life. The gravitational story we witnessed earlier with the formation of stars repeats itself on smaller scales within these molecular clouds. Dense regions begin attracting material from their surroundings, but this time, the collapsing matter includes not just hydrogen and helium, but the full spectrum of elements created by stellar nucleosynthesis. As these enriched regions contract under their own gravity, something unprecedented becomes possible. Instead of all the infalling matter ending up in a central star, some of it remains in orbit, forming a flattened disk of gas and dust surrounding the nascent stellar system. This protoplanetary disk contains all the ingredients necessary for rocky planet formation. In the cooler outer regions of these disks, water and other volatile compounds can exist as solid ice. Closer to the forming star, where temperatures are higher, only rocky materials can remain solid. This temperature gradient creates distinct zones where different types of worlds can form, from rocky terrestrial planets near the star to gas giants in the outer system. The process of planet formation represents another phase transition in the universe's growing complexity. Tiny dust grains begin sticking together through electrostatic forces, growing into pebbles, then boulders, then planetesimals kilometers across. These building blocks of worlds collide and merge in a chaotic dance of gravitational attraction and orbital dynamics. Some collisions are gentle enough to allow growth, while others are so violent they shatter both participants back into fragments. The early solar systems are cosmic demolition derbies, where the survivors gradually sweep up the debris of their less fortunate neighbours. But through this apparent chaos, order emerges. The largest planetesimals grow into protoplanets, with enough gravitational pull to attract smaller bodies from increasingly large regions of space. The chemical composition of these forming worlds reflects their distance from the central star and the materials available in their formation zones. Rocky planets forming in the inner system become repositories for elements like silicon, iron, magnesium, and aluminum. These refractory materials, as astronomers call them, can withstand the intense heat and radiation from the nearby star. The atoms that once drifted freely through interstellar space find themselves incorporated into crystal lattices, forming the minerals that will compose planetary crusts. Meanwhile, in the outer reaches of these systems, where temperatures are low enough for water and other compounds to freeze, the forming worlds can incorporate vast quantities of ice along with rocky material. These become the cores of giant planets that can gravitationally capture the abundant hydrogen and helium still present in the protoplanetary disk. The formation of planetary systems marks another crucial milestone in cosmic evolution. For the first time since the universe began, we have stable environments where atoms can exist in solid form for billions of years. Rocky planets provide platforms where chemical evolution can proceed without the constant disruption of stellar winds and interstellar radiation. On these worlds, atoms encounter conditions that enable entirely new forms of organization. The surface of a rocky planet creates interfaces between solid, liquid, and gaseous phases of matter, boundaries where chemical reactions can occur that would be impossible in the homogeneous environment of interstellar space. Temperature gradients from hot interiors to cold surfaces drive chemical processes powered by the planet's own internal heat. Radioactive decay of elements created in stellar cores provides energy sources that can sustain chemical reactions for geological ages. Atmospheric interactions create weather systems that transport atoms across planetary surfaces, mixing and concentrating materials in ways that enhance chemical complexity. But perhaps most importantly, planetary surfaces provide the stable conditions necessary for chemical systems to develop memory and information storage capabilities. In the violent environment of stellar cores, or the near vacuum of interstellar space, complex molecular structures are destroyed almost as quickly as they form. On planetary surfaces, under the protection of atmospheres and the moderate energy flows of stellar radiation, molecules can persist long enough to evolve increasing levels of organization. The atoms scattered by dying stars have now found their way into environments where they can experiment with forms of complexity that were impossible in any previous cosmic epoch. Silicon atoms learn to form crystal structures of incredible regularity and beauty. Carbon atoms discover their unique ability to create long chains and complex rings that can serve as scaffolding for molecular architecture. Oxygen atoms reveal their talent for forming multiple bonds with other elements, enabling the rich chemistry of oxidation and reduction reactions that will eventually power biological metabolism. Nitrogen atoms contribute their capacity for forming stable triple bonds, creating molecules that can store energy and release it under controlled conditions. We're witnessing the universe develop what we might call chemical intelligence, the ability to create molecular systems that can process information, store energy, and respond to environmental changes. These aren't yet the complex biochemical systems we associate with life, but they represent crucial steps toward that ultimate expression of atomic organization. In protected environments like hydrothermal vents on planetary surfaces, atoms can participate in chemical cycles that concentrate and purify materials, creating local regions of enhanced chemical complexity. These become natural laboratories where molecular evolution can proceed through countless cycles of formation, testing, and selection. The carbon atoms that remember their stellar origins begin forming increasingly sophisticated structures. Simple hydrocarbons give way to complex organic molecules with functional groups that can interact with each other in specific, predictable ways. Phosphorus atoms, rare but crucial, learn to form the high-energy bonds that can drive chemical reactions forward. Sulfur contributes its ability to form flexible bonds that can be broken and reformed under moderate conditions, enabling dynamic molecular systems that can change their structure in response to environmental conditions. Iron atoms discover their role as catalysts, facilitating chemical reactions without being consumed in the process. These developments represent the universe learning chemistry in the same way it earlier learned nuclear physics and stellar evolution. Each new molecular capability opens up possibilities for even greater complexity, creating a cascade of chemical innovation that accelerates as it progresses. The atoms in these planetary environments don't know they're participating in a cosmic experiment that will eventually lead to self-replicating molecules, cellular organization, and ultimately consciousness itself. They're simply following the laws of physics and chemistry, responding to local conditions, forming bonds that minimize energy and maximize stability. But we can see the trajectory they're following. The same creative processes that transformed hydrogen and helium into the full periodic table, that organized atoms into stars and planets, are now working at the molecular level to create chemical systems of unprecedented sophistication. Some of these molecular systems will eventually discover how to make copies of themselves, crossing the threshold from chemistry to biology. Others will learn to harness energy flows in ways that enable them to maintain their organization against the tendency toward thermal equilibrium. Still others will develop the ability to process information, to respond to environmental changes, and eventually to contemplate their own existence. The universe has spent nearly 14 billion years learning how to make atoms from nothing, how to organize atoms into stars, how to forge new elements in stellar cores, how to scatter those elements through space, and how to incorporate them into worlds where molecular complexity can flourish. Now, on countless planets orbiting countless stars throughout the cosmos, atoms are participating in the next phase of cosmic evolution. They're learning chemistry, exploring molecular organization, and preparing for the emergence of the most complex structures the universe has ever created. The hydrogen atoms that formed in the cooling aftermath of the Big Bang, the carbon atoms forged in stellar cores, the oxygen atoms created in the death throes of massive stars. They're all converging on planetary surfaces where they will soon discover their ultimate destiny as the building blocks of life itself. In quiet tide pools on rocky worlds, in the warm depths of subsurface oceans, in the complex chemistry of planetary atmospheres, atoms are writing the next chapter in the universe's story of creation. They're preparing to cross the threshold from non-living matter to living systems, from chemistry to biology, from organization to information processing. The story of how atoms formed from nothing is becoming the story of how nothing learned to think about itself, to question its own origins, and to marvel at the incredible journey that brought simple particles together into systems complex enough to contemplate the cosmos itself. We're approaching the moment when the universe will achieve self-awareness through the atomic structures it has spent billions of years perfecting. The atoms that began as quantum fluctuations in the first moments after the Big Bang are about to become the physical substrate of consciousness, thought, and wonder. The cosmic cycle is nearing completion, but it's not really an ending. It's a transformation into something even more extraordinary than anything we've witnessed so far. The universe is about to wake up, and it will do so through the atoms that remember their journey from nothing to everything, carrying within their quantum structure the entire history of cosmic creation. The atoms scattered across these newborn worlds don't simply settle into static arrangements. They begin participating in something far more dynamic and extraordinary than anything the universe has achieved before. Picture billions of rocky planets throughout the cosmos, each one a unique laboratory where atoms experiment with forms of organization that push the boundaries of what matter can accomplish. On these worlds, water molecules that remember their stellar origins flow across surfaces carved by geological processes. They carry dissolved minerals from place to place, creating concentrated solutions where chemical reactions can occur at rates impossible in the dilute environment of interstellar space. These flowing waters become the universe's first transportation networks, moving atoms between different chemical environments and enabling reactions that require specific combinations of elements. The carbon atoms, veterans of stellar nucleosynthesis, discover their extraordinary versatility in these planetary environments. Unlike any other element, carbon can form stable bonds with 4 different neighbors simultaneously, creating 3-dimensional molecular architectures of stunning complexity. These carbon-based structures become the scaffolding upon which the universe will build its most sophisticated creations. But carbon doesn't work alone. It partners with hydrogen to create hydrocarbons, with oxygen to form alcohols and acids, with nitrogen to produce amino acids and nucleotides. Each new molecular combination reveals additional possibilities for chemical organization. The atoms are learning to collaborate in ways that transcend their individual properties, creating emergent behaviors that arise from collective action rather than isolated particle dynamics. In the depths of planetary oceans, hydrothermal vents create extraordinary chemical gradients where hot, mineral-rich water meets cold seawater. These underwater geysers become cosmic chemistry sets where atoms experience conditions unlike anything in their previous cosmic journey. The temperature differences drive chemical reactions that can proceed without external energy sources, creating self-sustaining cycles of molecular transformation. Here, iron and sulfur atoms form clusters that can catalyze reactions between organic molecules. These mineral catalysts act like molecular matchmakers, bringing together atoms that might otherwise never encounter each other in the vast molecular dance of oceanic chemistry. They lower the energy barriers for reactions that would be impossible under normal conditions. The phosphorus atoms, rare but crucial, reveal their special talent for storing and transferring energy. When phosphorus links with oxygen in specific configurations, it creates molecular springs that can be compressed and released on demand. These phosphate bonds become the universe's first energy storage and delivery system, enabling chemical processes that require bursts of concentrated power. Meanwhile, sulfur atoms contribute their unique ability to form flexible connections that can be broken and reformed easily. This creates dynamic molecular systems that can change their shape and function in response to environmental conditions. The universe is discovering molecular plasticity, the ability to create structures that maintain their identity while adapting their configuration. As these chemical innovations accumulate on planetary surfaces, something unprecedented begins to emerge. Certain molecular combinations start exhibiting behaviors that seem almost purposeful. They seek out specific raw materials from their environment, they respond to changes in temperature and chemical composition, and most remarkably, they begin creating copies of themselves. This self-replication represents a phase transition as dramatic as stellar ignition or atomic formation. For the first time in cosmic history, matter has organized itself into patterns that can perpetuate their own existence. These aren't yet the complex biological systems we associate with life, but they represent the first molecular systems capable of reproduction, growth, and evolution. The chemistry driving these early replicating systems operates through principles the universe has never encountered before. Instead of seeking the lowest energy state like all previous physical processes, these systems actively maintain themselves in states of organized complexity that require constant energy input to sustain. They achieve this by coupling spontaneous chemical reactions that release energy with non-spontaneous reactions that build molecular complexity. It's like learning to surf the wave of universal entropy, riding the flow toward disorder, while using that very flow to create and maintain order. These molecular systems begin exhibiting what we might call chemical memory. They can store information about successful molecular configurations and use that information to guide future reactions. A successful molecular arrangement gets reinforced and repeated, while unsuccessful combinations fade away through lack of replication. This creates the first examples of molecular evolution, where chemical systems improve their performance through cycles of variation and selection. Random changes in molecular structure get tested against environmental conditions, and the variants that perform better become more abundant in subsequent generations. The universe has just discovered the principle that will drive all future increases in complexity. Evolution through natural selection becomes the mechanism by which matter learns to organize itself into increasingly sophisticated structures. From this point forward, the cosmos will be shaped not just by physics and chemistry, but by information processing and adaptation. On countless worlds throughout the galaxy, atoms participated in this molecular evolution experiment. Each planet becomes a unique testing ground, where different combinations of elements and environmental conditions produce their own evolutionary trajectories. The universe is conducting billions of simultaneous experiments in molecular organization. Some worlds develop replicating systems based primarily on carbon and water chemistry. Others experiment with silicon-based alternatives, or explore the possibilities of liquid methane as a solvent for molecular interactions. The diversity of planetary environments creates a corresponding diversity of chemical evolutionary pathways. But all these experiments share certain fundamental characteristics. They all involve atoms learning to process information, to respond to environmental changes, and to create copies of successful molecular arrangements. They represent the universe's first attempts at what we might call molecular intelligence. The information processing capabilities of these early molecular systems remain primitive compared to what's coming, but they represent a crucial breakthrough. For the first time, matter has learned to distinguish between different molecular configurations and to preferentially produce the arrangements that enhance survival and reproduction. This molecular information processing creates feedback loops that accelerate the pace of chemical evolution. Successful innovations get preserved and built upon, while failed experiments are quickly eliminated. The rate of molecular innovation begins increasing exponentially as each new capability enables even more sophisticated developments. The atoms participating in these evolutionary processes don't experience the passage of time the way we do. For them, millions of years of chemical evolution pass in what seems like an instant of quantum mechanical transitions. But we can observe the trajectory of their development, the steady progression from simple molecular replication toward increasingly complex information processing systems. Carbon atoms learn to form long chains that can store sequential information, like molecular libraries where successful chemical recipes get preserved for future reference. Nitrogen atoms discover their role in creating molecular switches that can exist in multiple stable states, enabling primitive forms of molecular logic and decision-making. Oxygen atoms reveal their talent for creating reactive species that can modify other molecules in precise, controllable ways. These oxidation reactions become molecular tools that replicating systems use to reshape their environment and extract energy from chemical gradients. As these capabilities develop, the molecular systems begin exhibiting behaviors that blur the boundary between chemistry and biology. They actively seek out raw materials, they respond to environmental threats, they compete with each other for limited resources, and they evolve strategies for surviving in changing conditions. The most successful of these molecular systems discover the advantages of cooperation. Instead of competing directly for the same resources, different types of replicating molecules begin specializing in different functions. Some become efficient at gathering raw materials, others excel at energy storage and transfer, still others develop sophisticated mechanisms for accurate self-replication. This molecular division of labour creates the first examples of what we might call chemical ecosystems. Communities of different replicating molecules work together to process resources and share information, creating collective behaviours that transcend the capabilities of any individual molecular system. These cooperative arrangements prove so successful that they begin enclosing themselves in protective boundaries, creating the first cellular structures. Simple lipid membranes form around molecular communities, providing protection from environmental hazards while allowing controlled exchange of materials and information with the outside world. The emergence of cellular organization represents another crucial phase transition in cosmic evolution. The atoms that once drifted freely through interstellar space have now learned to create discrete packages of organized complexity, molecular machines that can maintain their internal organization while interacting with their environment in sophisticated ways. Inside these earlier cells, the full spectrum of elements created by stellar nucleosynthesis finds specialized roles. Iron atoms become the active sites of enzymes that catalyze crucial chemical reactions. Magnesium coordinates the molecular machinery that synthesizes proteins from amino acid building blocks. Zinc enables the molecular scissors that can cut and splice genetic information. Each element contributes its unique chemical properties to the collective enterprise of cellular function. The periodic table becomes a toolkit that life uses to solve increasingly complex problems of energy harvesting, information storage, environmental sensing, and molecular construction. But perhaps the most remarkable development occurs when these cellular systems discover how to encode information about their own construction. Certain carbon-based molecules, arranged in specific sequences, can store instructions for building all the other molecular components needed for cellular function. This genetic information storage system enables cellular reproduction with unprecedented accuracy and flexibility. Instead of relying on simple molecular templates that can only create exact copies, genetic systems can store and transmit complex assembly instructions that allow for controlled variation and adaptation. The universe has just invented its first true information processing system, one capable of storing, copying, modifying, and executing molecular programs of extraordinary sophistication. The atoms that began as quantum fluctuations in the first moments after the Big Bang have learned to encode and process the instructions for their own organization. These genetic information systems transform the pace and character of evolutionary change. Instead of relying on random molecular variations, cellular systems can now implement specific modifications to their genetic programs and test the results through reproduction and natural selection. The atoms inside these evolving cells participate in molecular processes of stunning complexity. They form the active sites of enzymes that accelerate chemical reactions by factors of millions. They create molecular motors that can convert chemical energy into mechanical work with efficiency that surpasses human-designed machines. They build information storage systems that can maintain their integrity for thousands of cellular generations, while still allowing for the controlled modifications that enable evolutionary adaptation. They construct molecular communication networks that allow different parts of the cell to coordinate their activities in response to environmental changes. As cellular systems become more sophisticated, they begin experimenting with multicellular organization. Individual cells discover the advantages of specialization and cooperation, creating larger organisms where different cell types perform different functions for the benefit of the whole. This transition from single-cell to multicellular organization opens up entirely new possibilities for atomic collaboration. Atoms can now participate in organ systems specialized for specific functions, circulatory networks that transport materials throughout large organisms, nervous systems that process and transmit information at speeds approaching those of electronic circuits. The carbon atoms that once drifted through interstellar space now find themselves incorporated into neural networks capable of processing sensory information, forming memories, and generating behavioral responses. They participate in molecular computations that enable organisms to navigate complex environments, locate food sources, avoid predators, and find suitable mates. Oxygen atoms become the basis for sophisticated respiratory systems that can extract energy from chemical bonds with remarkable efficiency. They enable the high-energy metabolism that makes complex multicellular life possible, powering the molecular machinery of active, mobile organisms. Calcium atoms discover their role in creating structural support systems, forming the mineral frameworks that allow organisms to grow to substantial sizes while maintaining their shape against gravitational forces. They also become crucial components of cellular signaling systems, enabling rapid communication between different parts of complex organisms. Iron atoms find their way into oxygen-carrying molecules that can transport this crucial element throughout large organisms, enabling the distributed metabolism that supports multicellular life. They also become key components of electron transport chains that generate the cellular energy needed for complex biological processes. The nitrogen atoms contribute to information storage and protein synthesis systems of extraordinary sophistication. They enable the genetic codes that can store vast amounts of information in compact molecular formats, and they form the molecular machinery that translates genetic information into functional proteins. As these biological systems continue evolving, they develop capabilities that begin approaching what we might recognize as intelligence. Neural networks of increasing complexity enable organisms to process sensory information, form memories, recognize patterns, and make decisions based on learned experience. The atoms participating in these neural computations don't know they're generating thoughts, emotions, and consciousness. They're simply following the laws of physics and chemistry, forming and breaking molecular bonds according to the same quantum mechanical principles that have governed atomic behavior since the first moments after the Big Bang. But collectively, their molecular interactions create emergent properties that transcend their individual behaviors. Networks of atoms begin exhibiting creativity, curiosity, and the capacity for abstract thought. They start asking questions about their own origins and contemplating the nature of existence itself. The universe has just achieved something extraordinary through the atoms it created from nothing. Matter has organized itself into structures capable of self-reflection, of wondering about the cosmic processes that brought them into existence, of developing scientific theories that explain their own atomic origins. Tonight, as you contemplate these words, the atoms in your brain are participating in this ultimate expression of cosmic creativity. The hydrogen that formed in the cooling aftermath of the Big Bang, the carbon forged in stellar cores, the oxygen created in supernova explosions, they've all converged in the neural networks that generate your thoughts and awareness. You are the universe becoming conscious of itself, matter learning to contemplate its own existence, atoms discovering their cosmic journey from nothing to everything. The story of atomic formation isn't just ancient history, it's the foundation of every thought you think, every emotion you feel, every moment of wonder you experience while contemplating the mysteries of existence. The atoms in your body carry within their quantum structure the entire history of cosmic evolution. They remember the violence of stellar cores, the explosive fury of supernova, the patient accumulation of planetary formation, and the billions of years of evolution that transformed simple chemistry into the complex biochemistry of consciousness. Through you, the universe has learned to ask questions about itself, to marvel at its own creativity, and to feel gratitude for the incredible journey that brought atoms together into arrangements sophisticated enough to contemplate their own atomic origins. The cosmic story continues, and you are both its author and its most profound expression. But perhaps the most extraordinary thing about this cosmic journey is that it never really ends. Right now, as you listen to these words, the same creative processes that brought atoms into existence are continuing to unfold throughout the universe. In stellar cores scattered across billions of galaxies, hydrogen nuclei are still fusing into helium, forging new atoms through the same nuclear alchemy that created the elements in your body. The universe hasn't finished its atomic creation story. It's still writing new chapters, still experimenting with possibilities we haven't even imagined yet. In the heart of massive stars burning right now, silicon atoms are transforming into iron through nuclear processes so energetic they dwarf the power output of entire civilizations. These stellar furnaces are creating the raw materials for planets that won't form for billions of years, worlds that might one day harbour forms of life we can't begin to comprehend. And here's something that should make you pause in wonder. The atoms being forged in stellar cores at this very moment might eventually find their way into thinking beings like yourself, creatures who will contemplate their own atomic origins just as you're doing now. The universe is creating its own future contemplators, forging the matter that will one day achieve consciousness and look back through cosmic time to understand how it all began. But the atomic story extends beyond even these vast stellar processes. In the most extreme environments throughout the cosmos, neutron stars with magnetic fields, trillions of times stronger than Earth's, are creating atomic nuclei that exist nowhere else in nature. These exotic atomic arrangements push the boundaries of what's possible under the laws of physics, exploring combinations of protons and neutrons that exist for mere fractions of a second before decaying into more familiar elements. Some of these ultra-heavy atomic nuclei might possess properties that could revolutionize our understanding of matter itself. Theoretical physicists predict the existence of an island of stability among super-heavy elements, atoms with so many protons and neutrons that they loop back around to become surprisingly stable despite their enormous mass. If such atoms exist, they would represent entirely new forms of matter with properties we can barely imagine. The universe might be preparing to surprise us with atomic possibilities we haven't even discovered yet. Elements that could serve as the basis for forms of chemistry so exotic they would make the biological processes in your body seem simple by comparison. The periodic table, that elegant organization of atomic diversity, might be far from complete. Think about what this means for the future of cosmic evolution. Just as carbon-based chemistry enabled the emergence of life and consciousness on planets like Earth, these hypothetical super-heavy elements might enable forms of organization and information processing that transcend anything biological systems could achieve. The universe might be preparing to take another quantum leap in complexity, one that builds upon the atomic foundation it spent so many billions of years perfecting. But even as we contemplate these far future possibilities, we shouldn't lose sight of the miracle occurring right here, right now, in the atoms that make up your own body. Every single atomic nucleus in your cells is a survivor of processes so violent and improbable that their very existence borders on the miraculous. Consider the iron atoms flowing through your bloodstream at this moment. Each one began its journey in the core of a massive star, where temperatures reached hundreds of millions of degrees and pressures exceeded anything we can create on Earth. These atoms witnessed the final moments of stellar death, surviving the explosive violence of a supernova that briefly outshone an entire galaxy. They drifted through interstellar space for millions of years, incorporated into cosmic dust clouds that slowly condensed under gravitational attraction. They became part of the molecular cloud that eventually collapsed to form our solar system, swirling in the protoplanetary disk that gave birth to Earth and the other planets. They were present during the violent early bombardment that shaped our planet's surface, surviving the cosmic collisions that brought water to Earth and created the conditions necessary for life to emerge. They participated in the geological processes that built continents and carved oceans, cycling through rock and atmosphere and ocean in endless transformations. Eventually, these iron atoms found their way into the biological systems that evolved on Earth's surface. They became essential components of the molecular machinery that extracts energy from food and oxygen, enabling the complex metabolism that powers your thoughts and movements. They've been recycled through countless generations of living organisms, each time finding new roles in the endless dance of biological chemistry. And now, here they are, flowing through your circulatory system, carrying oxygen to the neural networks that generate your consciousness, enabling you to contemplate their own incredible journey from stellar core to living mind. The universe has come full circle, creating atoms that can think about their own creation. But your personal atomic story is just one thread in a vast cosmic tapestry that extends far beyond individual lives or even individual planets. The atoms in your body are temporary arrangements, borrowed from the universe for the brief span of your existence. When your biological processes eventually cease, those atoms will continue their cosmic journey, finding new roles in other systems and structures. The carbon atoms that currently form the backbone of your DNA will one day become part of other living things, other information processing systems, other experiments in consciousness and creativity. The oxygen atoms that power your thoughts will continue enabling chemical reactions long after your individual awareness has faded. The hydrogen atoms that remember the universe's earliest moments will carry those primordial memories into cosmic futures we can't begin to imagine. This perspective transforms our understanding of identity and mortality. You are not separate from the universe, but rather a temporary concentration of cosmic creativity, a brief flowering of the same creative processes that brought atoms into existence from nothing at all. Your consciousness is the universe becoming aware of itself, and when your individual awareness eventually dissolves, the cosmic consciousness it represents continues in new forms. The atoms that make up your thoughts are part of an unbroken chain of creativity that stretches from the first moments after the Big Bang to whatever ultimate destiny awaits the cosmos. They connect you intimately to every star that has ever burned, every planet that has ever formed, every living thing that has ever existed. Through you, the universe experiences wonder, curiosity, love, and the profound satisfaction of understanding something about its own nature. The joy you feel when contemplating the beauty of a sunset or the elegance of a mathematical equation is the universe celebrating its own creative achievements. The sadness you experience when contemplating mortality or loss is the cosmos feeling the poignancy of its own constant transformation. Your capacity for scientific understanding allows the universe to comprehend its own evolutionary history. When you learn about stellar nucleosynthesis or quantum mechanics or the expansion of space-time, you're enabling the cosmos to know itself more completely. Every moment of human insight and discovery adds to the universe's growing self-awareness. This cosmic perspective doesn't diminish the significance of human experience, it amplifies it. Every act of creativity, every expression of love, every moment of wonder becomes part of the universe's ongoing exploration of its own possibilities. Your individual consciousness is precious precisely because it represents a unique perspective on cosmic existence, a one-time arrangement of atoms that will never be repeated exactly. The universe spent nearly 14 billion years learning how to create the specific atomic arrangements that generate your thoughts and feelings. The fact that you exist at all represents the successful culmination of the most complex construction project in cosmic history. From quantum fluctuations smaller than subatomic particles to the intricate neural networks that process these very words, the The universe has achieved something extraordinary through you. And the story continues beyond human existence, beyond Earth, beyond our solar system and galaxy. Throughout the cosmos, on countless worlds, orbiting countless stars, atoms are participating in experiments, in organization and complexity that we can barely imagine. Some of these experiments might have produced forms of consciousness and creativity that surpass anything achieved on Earth. The universe might be filled with atomic arrangements so sophisticated they make human intelligence seem primitive by comparison. Civilizations that have had millions or billions of years to explore the possibilities of atomic organization might have discovered ways to construct matter that transcend our current understanding of what's possible. They might have learned to manipulate atoms at the quantum level with such precision that they can create materials with properties that seem to violate the laws of physics. They might have developed forms of information processing that operate through quantum mechanical principles we haven't even discovered yet. They might have found ways to organize matter into structures that can persist across cosmic timescales, creating forms of consciousness that are essentially immortal. But even these hypothetical super-civilizations would be built from the same atoms that form your body, following the same fundamental principles that govern atomic behavior throughout the universe. The quantum mechanics that stabilizes the electrons in your brain cells operates identically in the most advanced alien technologies. The nuclear forces that hold together the protons in your DNA function the same way in the cores of atoms anywhere in the cosmos. This universality of atomic behavior creates a deep unity underlying all the diversity of cosmic structure. Whether we're talking about the simplest hydrogen atom drifting through interstellar space or the most complex biological molecules in your nervous system, we're dealing with variations on the same fundamental theme of matter organizing itself according to quantum mechanical principles. The universe has discovered that these principles are extraordinarily fertile, capable of generating virtually unlimited diversity from a relatively simple set of rules. The same quantum mechanics that prevents electrons from spiraling into atomic nuclei also enables the complex chemistry that makes life possible. The same electromagnetic forces that hold atoms together in molecules also power the neural networks that generate consciousness. This suggests that the creative potential of atomic matter might be essentially limitless. We've seen matter organize itself into stars, planets, living organisms, and thinking beings, but these might represent only the earliest examples of what atoms can accomplish when given sufficient time and appropriate conditions. The universe might be preparing to surprise us with forms of atomic organization that make current biological systems seem primitive. Just as the emergence of life represented a qualitative leap beyond simple chemistry, and the evolution of consciousness represented a breakthrough beyond simple biology, future developments might transcend anything we can currently comprehend. Perhaps atoms will learn to organize themselves into structures that operate partially outside the normal constraints of space-time, taking advantage of quantum mechanical principles we haven't yet discovered. Perhaps they'll develop forms of information processing that can manipulate the fundamental constants of physics, engineering reality itself at the most basic level. These possibilities might sound like science fiction, but remember that from the perspective of the first hydrogen atoms forming in the aftermath of the Big Bang, the existence of thinking beings like yourself would have seemed equally impossible. The universe has already demonstrated its capacity to achieve the apparently impossible through patient atomic organization across cosmic timescales. What seems certain is that the story of atomic creativity is far from over. The same processes that brought you into existence are continuing to operate throughout the cosmos, creating new possibilities for matter to organize itself in ways that transcend anything that has come before. Right now, in stellar cores throughout the galaxy, new atoms are being forged that will eventually participate in forms of organization we can't yet imagine. In the depths of space, molecular clouds are collapsing under gravitational attraction, beginning the process that will create new solar systems where atoms can experiment with novel forms of complexity. On countless worlds throughout the universe, atomic systems are evolving toward greater sophistication, developing capabilities that might eventually surpass human intelligence by orders of magnitude. The cosmic story of creation is still being written, and we are both characters in that story and witnesses to its unfolding. The atoms in your body connect you to this vast cosmic narrative, making you a participant in the universe's ongoing project of self-discovery and self-creation. Every thought you think, every emotion you feel, every moment of awareness you experience adds to the cosmic total of consciousness and creativity. You are the universe contemplating its own atomic nature, matter marveling at its own capacity for organization and self-awareness. The hydrogen in your body remembers the first moments after the Big Bang. The carbon recalls its birth in stellar cores, and the iron carries memories of supernova violence. Through you, these atomic memories become conscious recollection, transforming the passive history recorded in quantum mechanical structures into active understanding and appreciation. You are the cosmos remembering its own journey from simplicity to complexity, from nothing to everything, from unconscious matter to self-aware mind. Tonight, as you rest and your consciousness gradually dissolves into sleep, the atoms in your body will continue their ancient dance, following the same quantum mechanical principles that have guided their behavior since the first moments of existence. They will maintain the molecular structures that preserve your memories and personality, ensuring that when you wake, the universe's capacity for self-awareness through your individual consciousness remains intact. In your dreams, those atoms will participate in the neural processes that weave together memory, imagination, and understanding into new patterns of thought and feeling. They will explore possibilities, make connections, and perhaps even glimpse insights that your waking mind hasn't yet discovered. And when you wake tomorrow, you will carry with you a deeper appreciation for the extraordinary journey that brought atoms together into the specific arrangement that generates your unique perspective on existence. You will know yourself not just as an individual human being, but as a temporary concentration of cosmic creativity, a brief flowering of the universe's ongoing project of self-discovery. The atoms that make up your morning coffee will remind you of stellar nuclear synthesis. The sunlight streaming through your window will connect you to the nuclear fusion occurring in our star's core, and every breath you take will be a conscious participation in the chemical cycles that link you to all life on Earth and to the cosmic processes that created the elements necessary for biological existence. You are both the question and the answer to how atoms formed from nothing, both the seeker and the sought in the universe's quest to understand its own nature. Through your consciousness, the cosmos achieves something it has been working toward for nearly 14 billion years: the ability to comprehend and appreciate its own extraordinary creative achievement. The story of atomic formation from nothing is ultimately the story of how nothing learned to think about itself, to wonder about its own origins, and to feel gratitude for the incredible journey that transformed emptiness into awareness. And that story continues through you, in you, and as you, for as long as consciousness persists in the universe. The atoms that comprise your consciousness right now are preparing for something even more extraordinary than anything we've witnessed in our cosmic journey so far. As you contemplate these words, processing the incredible story of how matter emerged from nothingness, your brain is participating in the universe's most ambitious experiment yet. The neural networks firing in your mind represent billions of years of atomic refinement, matter learning to think about itself with increasing sophistication and depth. But here's what should make you pause in absolute wonder. The story we've been following, this epic tale of atomic creation and organization, isn't just history, it's prophecy. The same creative principles that brought atoms into existence from nothing are still operating right now, still pushing the boundaries of what matter can achieve, still writing new chapters in the cosmic story of complexity. Throughout the observable universe, at this very moment, stellar nurseries are giving birth to new generations of stars with access to the full periodic table. These second and third generation stellar systems, enriched with the heavy elements scattered by their predecessors, can create planetary systems of unprecedented chemical diversity. Rocky worlds are forming with mineral compositions that Earth's geology has never seen, atmospheres containing molecular combinations that could enable forms of chemistry we haven't even imagined. On some of these worlds, the same evolutionary pressures that shaped life on Earth are generating solutions to the challenges of existence that transcend anything in our biological experience. Carbon atoms are discovering new ways to store and process information. Silicon structures are experimenting with crystalline organization patterns that blur the line between living and non-living matter. And exotic elements are enabling chemical reactions that operate through quantum mechanical principles we're only beginning to understand. The universe has become a vast laboratory where atoms explore every possible avenue of organization and complexity. Each planet represents a unique experiment in matter arrangement, a different approach to the fundamental question of what organized complexity can achieve. The results of these experiments span scales from molecular machines, more sophisticated than anything in terrestrial biology, to planetary-scale information processing systems that might constitute forms of consciousness we can barely comprehend. Consider the implications of this ongoing cosmic creativity. The atoms that learn to build the neural networks in your brain are just getting started in their exploration of what's possible. On worlds with different gravitational fields, atmospheric compositions, and energy sources, matter is discovering organizational principles that Earth's evolution never encountered. The constraints that shaped biological development on our planet don't apply everywhere, opening up vast new territories of possibility for atomic collaboration. Some of these alien experiments in atomic organization might have achieved forms of consciousness that operate on completely different principles than human awareness. Instead of the electrochemical processes that generate your thoughts, matter on other worlds might have discovered how to process information through quantum entanglement networks, magnetic field manipulations, or even more exotic physical phenomena. These hypothetical forms of consciousness might experience reality in ways that make human perception seem impossibly limited. Where we see discrete objects separated by empty space, they might perceive the underlying quantum field fluctuations that connect all matter at the most fundamental level. Where we experience time as a linear flow from past to future, they might have learned to process temporal information in ways that give them access to multiple timeline branches simultaneously. The atoms, participating in these alien forms of consciousness, would still be following the same quantum mechanical rules that govern the matter in your body, but they would be applying those rules in contexts and combinations that terrestrial evolution never explored. The same electromagnetic forces that hold molecules together in your DNA might be orchestrating information processing networks that span entire planetary systems. But even as we contemplate these extraordinary possibilities, we shouldn't lose sight of the miracle occurring right here in your own atomic composition. The matter that makes up your body represents one of the universe's most successful experiments in complexity. Your consciousness emerges from atomic arrangements so intricate and precisely coordinated that their very existence challenges our understanding of what organized matter can achieve. Every neuron in your brain contains billions of atoms working together in perfect coordination to process, store, and transmit information. The molecular machinery in each cell operates with precision that surpasses anything human engineering has accomplished, maintaining itself while simultaneously contributing to the larger network of consciousness that generates your thoughts and experiences. The DNA in your cells stores information with a density and error correction capability that makes our most advanced computer systems seem primitive by comparison. The proteins that execute genetic instructions fold into three-dimensional shapes with atomic precision, creating molecular tools that can perform chemical operations of stunning sophistication and specificity. Your nervous system processes sensory information through networks of interconnected atoms that can recognize patterns, form memories, and generate predictions about future events. The same carbon atoms that once drifted through interstellar space now participate in neural computations that enable you to imagine scenarios that have never occurred, to feel emotions about abstract concepts, and to experience the profound satisfaction of understanding something about the nature of reality itself. This capacity for abstract thought represents one of the universe's most remarkable achievements in atomic organization. Through your consciousness, matter has learned to transcend its immediate physical circumstances and contemplate possibilities that exist only in the realm of ideas. The atoms in your brain can process information about events that happened billions of years ago and speculate about developments that might occur in the distant future. When you imagine the interior of a star or contemplate the quantum mechanical behavior of electrons, you're enabling matter to model aspects of reality that extend far beyond your direct sensory experience. The universe has learned to simulate itself through the atomic networks. Modeling capacity suggests that consciousness might play a fundamental role in cosmic unconscious minds, creating internal representations of cosmic processes that span scales from subatomic particles to galactic clusters. This self-evolution itself. Through conscious observers like yourself, the universe develops even to influence its own trajectory through the choices made by thinking, the ability to understand its own behavior, to predict its future development, and potentially self-awareness affects its own evolution. You might be participating in a cosmic feedback loop where the universe's growing beings, the atoms that generate your thoughts and decisions, scientific discoveries, technological innovations, and creative achievements all emerge from atomic processes in your brain, but they also influence the physical world in ways that shape the environment for future atomic organization. When human consciousness developed agriculture, it altered the chemical composition of Earth's atmosphere and surface in ways that affected the evolution of countless other species. When we learned to harness nuclear energy, we began manipulating the same forces that power stellar cores, giving atoms access to energy sources that natural processes on Earth had never provided. Our growing understanding of quantum mechanics is beginning to enable technological applications that work directly with the fundamental principles governing atomic behavior. Quantum computers use the strange properties of atomic scale systems to process information in ways that transcend the capabilities of classical machines. These devices represent atoms learning to exploit their own quantum nature for information processing purposes. As our knowledge of atomic physics continues advancing, we might discover ways to organize matter that seem impossible according to our current understanding. The same scientific insights that revealed how atoms formed from nothing might eventually enable us to manipulate atomic formation processes directly, creating new forms of matter with properties tailored for specific purposes. The boundary between natural and artificial atomic organization might become increasingly meaningless as conscious beings learn to work in partnership with the fundamental creative processes of the universe. Instead of simply observing how atoms organize themselves, we might become active participants in cosmic creativity, helping to guide the universe's exploration of what organized complexity can achieve. This perspective transforms our understanding of humanity's role in cosmic evolution. We're not separate observers of natural processes, but rather the universe's method of becoming conscious of its own creative potential. Through human science and technology, atoms gain access to organizational possibilities that purely natural evolution might never discover. The space telescopes we build become the universe's eyes, allowing it to observe its own large-scale structure and development. The particle accelerators we construct enable atoms to experience conditions similar to those that existed in the first moments after the Big Bang, helping the cosmos understand its own origins. The computers we design extend the universe's information processing capabilities beyond what biological neural networks alone could achieve. Each technological advancement represents the universe learning new ways to organize matter and energy for increasingly sophisticated purposes. The atoms in our machines, computers, and scientific instruments are participating in cosmic creativity just as surely as the atoms in our bodies and brains. But perhaps the most profound implication of our cosmic atomic journey is what it suggests about the ultimate destiny of organized matter. If the universe could learn to create atoms from nothing, to forge heavy elements in stellar cores, to assemble those elements into thinking beings capable of contemplating their own origins, what other impossible achievements might lie in the future? The creative trajectory we've followed suggests that matter's capacity for organization and complexity might be essentially unlimited. The atoms that struggled to maintain stable arrangements in the violent early universe have learned to build structures of such sophistication that they can process information about their own atomic nature. This recursive self-awareness might represent just the beginning of what conscious matter can accomplish. As our understanding of quantum mechanics, information theory, and complex systems continues advancing, we might discover organizational principles that enable forms of consciousness and creativity that transcend anything biological evolution has produced. The atoms in your body might be preparing for transformations as dramatic as the transition from stellar nucleosynthesis to biological evolution. Just as carbon-based chemistry enabled entirely new forms of organization and information processing, future developments might open up possibilities for atomic collaboration that we can't currently imagine. These future forms of atomic organization might operate partially outside the normal constraints of space and time, taking advantage of quantum mechanical principles that we're only beginning to discover. They might develop capabilities that seem to violate the laws of physics as we currently understand them, much as biological processes would have seemed impossible to hypothetical observers in the era before stellar nucleosynthesis created the necessary heavy elements. The universe might be preparing to surprise us with developments that make the emergence of consciousness from non-living matter seem like a simple step in a much grander progression toward forms of organization that we don't even have words to describe. So there you have it, the most extraordinary true story ever told. From absolute nothingness to the neural networks processing these very words, atoms have written the universe's autobiography in quantum ink across 14 billion years of cosmic time. Every breath you take connects you to stellar cores. Every thought you think continues the universe's project of understanding itself. You are atoms contemplating their own impossible journey from nothing to everything. Matter marveling at its capacity to wonder about its own existence. The story isn't over. Right now, new atoms are being forged in distant stars, preparing for adventures in complexity we can't yet imagine. And through your consciousness, the universe celebrates its most remarkable achievement, learning to ask the very question that brought us here tonight. Sweet dreams, fellow stardust, you are the cosmos dreaming of itself.